So here we're going to look at a nice problem that didn't quite make the International Math Olympiad. So this is from the 1996 shortlist. And our goal is to find all natural numbers a and b. So by natural numbers, I mean positive integers, satisfying the following equation that involves the floor function. So we've got this floor of a squared over b plus the floor of b squared over a equals the floor of a squared plus b squared over ab plus ab. And this is actually pretty involved. And I didn't come up with a lot of really good hints for this solution, so we're going to jump right into the solution. So notice that without loss of generality, we can assume that A is bigger than or equal to B, well, and B is bigger than or equal to 1 as well. And why can we do that? Well, we can do that because of the symmetry in the equation of switching A with B. So if we find a set of solutions where A is bigger than or equal to B, then we can just permute A and B and we'll have a set of solutions when B is bigger than or equal to A. So we might as well just focus on this single setup where we know this ordering here. Okay, great. Now let's maybe look at our first case. So case number 1 would be A equals B. So if we're assuming that A is bigger than or equal to B, well then A could be equal to B. That is one possibility. So let's see what our goal equation is under that setup. So here we're going to have the floor of A squared over A plus the floor of A squared over A equals the floor of A squared plus A squared over A squared plus A squared. So notice I just replaced all of the B's with A and we got something like that. But notice this is going to simplify quite a bit. So this A squared over A is going to become just A. This one will become just A as well. This one right here will become 2. Now we've got to take the floor of all those, but we're assuming that they're natural numbers, so the floor doesn't do anything. So here we'll have A plus A equals 2 plus A squared, like that. But notice that is going to give us 2A equals 2 plus A squared. Now you can check the solutions to this quadratic equation, but one pretty obvious truth once you look into it is there are no solutions to this quadratic equation with A in the natural numbers. And you can do that a bunch of different ways, so we're not going to check that here, but that's pretty easy to check. Okay, so that means that we can't have this setup where A is equal to B, so that means we must have that A is strictly bigger than B, or the symmetric case where B is strictly bigger than A, but we'll get that for free after analyzing the setup when A is bigger than B. Okay, so let's maybe get to that case. Okay, so we've already determined that we cannot have A equal to B. And without loss of generality, we've assumed that one is bigger than the other. Here we've assumed that B is bigger than A. Now we're gonna build some inequalities to really get a handle on the relationship between A and B. So I first want to notice that A times B, well, that's going to be something inside of our equation. Notice on the right-hand side of the equation. Really, the question is, can we write this in terms of some stuff that is in the equation somewhere else? And we can. Notice if we take the product of these two things within the floor function, we get A times B. So let's maybe write that down just without the floor function for a second and see if that helps us at all. So notice A times B, well, that's going to be the same thing as A squared over B times B squared over A. Just by simple arithmetic simplification. Okay, but this doesn't have anything with the floor. Sure, we've written one part of the equation in terms of other pieces of the equation, but we've forgotten the floor function. But the floor function can only make things less than or equal to. Remember, it's an elevator downstairs to the closest integer. So that means we could include the floor function on each of these terms if we introduce an inequality. So this is going to be bigger than or equal to the floor of A squared over B times the floor of B squared over A. And that's actually really good news because now we've got an inequality relating parts that are inside our original equation. Okay, so now we just have to get a handle on this object right here. Can we get some sort of inequality involving this object? And we can, and I think probably if you're like a well-trained math contest problem solver, you can just write down the inequality for this real quick, but we're gonna derive it. So let's notice first that a minus b quantity squared is most definitely bigger than or equal to 0. Well, if we square any real number, that's always going to be bigger than or equal to 0. So we don't really have to think about that so much. But now let's FOIL this out. We'll get a squared minus 2ab plus b squared is bigger than or equal to 0. So next what we can do is maybe add 2ab to both sides. So we get a squared plus b squared is bigger than or equal to 2ab. Next, we know that a and b are both positive, so if we divide by a times b, we're dividing by a positive number, so that does not change the direction of the inequality, so that gives us a squared plus b squared over ab is bigger than or equal to 2. And so that's good news as well, because now we've got an inequality that involves this other term from the goal equation. Okay, so let's maybe just reiterate what we've got here. So we've got this inequality here, which is relating terms that look like this from the goal equation, and then this inequality here, which has a term that looks like that from the goal equation. Now we want to try to glue those together to maybe something that is a bit more helpful for our goal. So let's maybe go ahead and start with the goal equation. So that's going to be a squared over b plus floor of b squared over a equals floor of a squared plus b squared over ab, and then plus ab. Now we can apply the inequalities. So notice that we know that ab is going to be bigger than or equal to this object. Okay, so that's cool. And we also know that a squared plus b squared over ab is going to be bigger than or equal to 2. Well, the floor is a non-decreasing function, so, or a weakly increasing function, so we can replace this thing in the floor with 2, and we're definitely going to be bigger than or equal to. So that's what we'll do for each of these. So just to reiterate, I'm going to replace this thing in here with the inequality that I derived in the pink underline, and this thing right here with the inequality that I've derived with the green underline. So that's going to give us something that's bigger than or equal to the floor of 2 plus the floor of a squared over b squared times b squared over a, like that. And that's actually a little bit more helpful than it might seem, because we can move this stuff around and make a factorable inequality. So first I want to notice that this floor of 2 is just the number 2. We don't really need to worry about that too much. Okay, so next I'm going to move everything around so that I have a -1 on one side of the inequality. So let's write that down and maybe talk why that is a nice thing to do. Oh, I noticed I've got an extra b there. Let's erase that. So we'll have a squared over b times floor of b squared over a minus floor of a squared over b minus floor of b squared over a plus 1 is going to be less than or equal to -1. Okay, so what did I do here? Well, I subtracted each of these to the other side of the inequality, then I subtracted 1 from both sides of the inequality, and then I wrote it in a slightly different order. And this is helpful because we know that a and b are both natural numbers, but now we've got that this is less than or equal to -1, so that actually gives us a lot of power here. Also, this thing on the left is factorable. So I want to notice that this thing on the left is of the form xy minus x minus y plus 1. So if you look at it like that, you can see that it's factorable. And I think this is like a fairly standard factorization trick that happens in these contest problems. And I have to admit, like, yeah, I knew how to factor that before I did all of these contest problems. But since like making all these contest problem videos, I've noticed that this factorization shows up all the time. Okay, so anyway, we're gonna get the floor of a squared over b minus 1 times the floor of b squared over a minus 1 is going to be less than or equal to -1. Now, I want to notice that I've got up here this assumption that a is bigger than b. So the fact that a is bigger than b will tell us that this object right here is going to be bigger than or equal to 0. But the fact that this object right here is bigger than or equal to 0, but that product is less than or equal to -1, well, I mean, that's really good news because that tells us that this thing right here is strictly less than 0. In other words, that thing right there is negative. So let's see what that tells us. That gives us maybe more information than we might think initially. So we've got the floor of b squared over a minus 1 is less than 0. But that tells us that the floor of b squared over a is going to be less than 1. Okay, but if the floor function is giving you something that's less than 1, and I should point out that this is the quotient of two natural numbers in there, so that's also bigger than or equal to 0. So we've pinned a floor between 0 and 1, but not including 1. But what that tells us is that this floor is equal to 0. In other words, b squared over a is less than 1, which tells us that b squared is less than a. But now if b squared is less than a, that tells us that a can be written as b squared plus m for some natural number m. Okay, and maybe that's a good ending point for this chalkboard. So let's maybe go ahead and bring that up and we'll move on. Okay, what have we done so far? We first showed that a cannot be equal to b. Then without loss of generality, we decided that a could be bigger than b. And that implied that a was actually bigger than b squared. So we could write a as b squared plus some other natural number m. Now we're going to chuck this version of a back into our goal equation and see what happens. So let's see what we'll get. We're going to have b squared plus m quantity squared over b. So that's what we get for this first guy. And then next we'll have b squared over b squared plus m quantity squared. Sorry, not quantity squared, just b squared plus m, like that. So that would be this term. And then next, we're going to have that is equal to the floor of b squared plus m all squared plus b squared over, well, we've got b times b squared plus m, so that's going to be b cubed plus mb, like that. And then we've got plus a times b, so that's going to be another b cubed plus mb. Okay, nice. Now, well, m is a natural number, which makes the denominator here larger than the numerator. Since the denominator is larger than the numerator, the interior of that floor is going to be between 0 and 1, not including 1, which tells us that this whole thing goes off to 0. Well, it is 0. Okay, now let's expand this thing a little bit to see if we can simplify. So that's going to give us b to the 4th plus 2b squared m plus m squared. And then this is going to be over b, and then this is also going to be over b, like that. And then that's also still in the floor function. I wrote it like that because here we can cancel this b with this 4th power, and it's going to become a 3rd power, and this 2nd power, and it's going to become a 1st power. And so that writes this stuff inside the floor as a natural number plus a fraction, so we can extract that natural number. So maybe we'll do that in the next step. Okay, then we can also multiply out this numerator here. So let's see what that's going to give us. That's going to give us b to the 4th plus 2 mb squared plus m squared plus b squared. Then this is going to be all over b cubed plus mb. And then on the outside, we still have b cubed plus mb, like that. Okay, great. Now let's see, we talked about before how this stuff, which I'm putting in green parentheses, that's a natural number. So since it's a natural number, that can just be pulled out of the floor function. So let's do that. We've got b cubed plus 2mb. I'll maybe commute the b and m just so that they match the way I've written it otherwise. And then next I've got plus the floor of m squared over b equals. So now let's see if we can do any simplification of this next term like we did this term right here. So what we would maybe like to do is factor part out of it that will cancel with the denominator. So let's see what that would be. So maybe we could rewrite this as b times b cubed plus mb over b cubed plus mb. So that's taking some of the terms from the numerator. Notice that's taking a b times b cubed, the b to the fourth term. And then it's taking this b times mb. It's taking one of these 2 times mb squared terms. We don't want to take both of the mb squared terms because if we did that, then we wouldn't be able to cancel this denominator. Now let's see what's left over in the numerator after doing that. So what we get in the numerator looks like this. We'll have b squared, and then we'll have times m plus 1 times m squared. Now this is all over that same thing in the denominator. Then plus b cubed plus mb. That's what we have outside of the floor. Okay, so that's good news. So let's see what we've got. This thing can cancel with this thing, leaving us with b. We can pull that b out of the floor. Now let's do some simplification. This b cubed on the left can cancel this b cubed on the right. This mb on the right can cancel the coefficient 2 down to a 1 on the left. So we're left with something like that. And then next, since we've canceled this numerator and this denominator, we can bring this b out of the floor because, again, we know that's a whole number. Okay, so let's see what we've got here. So we're going to have m times b plus floor m squared over b equals b plus the floor of b squared m plus 1 plus m squared. I just noticed I had a typo there. That should be plus m squared all over b cubed plus mb. Okay, so that reduces our equation to this thing right here. Okay, maybe I'll go ahead and bring that to the top and we'll keep going. Under our setup where a was equal to b squared plus 1, we've reduced our goal equation to the following equation. Now it's time to start to look for some low-hanging fruit. In other words, maybe some nice values of m that would make this have a solution. And then probably after we find those nice values of m, you can see that no other values will really give us a solution. So let's maybe check the nicest value of m. Remember, m is a natural number here. So let's maybe go ahead and check the m equals 1 value and see if we can find some values of b that are companions of this value of m. So let's see what we get over here. So that's going to be b plus, now we've got the floor of 1 over b equals b plus the floor of, so we've got m plus 1, that's going to be 2b squared plus 1 all over b cubed plus b, like that. Okay, so now I want to notice that I can go ahead and cancel these b's from both sides, and we're left with this new equation. The floor of 1 over b equals the floor of 2b squared plus 1 over b cubed plus 1. Now next, I want to notice that if b is bigger than or equal to 2, then this left-hand side is equal to 0, because I've got the floor of a half or the floor of a third or anything like that. Then let's maybe go ahead and check what we get for the right-hand side if b is bigger than or equal to 2. Well, notice if b is bigger than or equal to 2, then this numerator is going to be smaller than the denominator, because 2b squared is going to be strictly less than b cubed because I multiply by an extra b, which is bigger than or equal to 2. And then b is bigger than or equal to 2, so adding b is more than adding 1. So in other words, this denominator is bigger than the numerator, so that this right-hand side is also equal to 0. So that's good news. If we've got m equals 1 and b bigger than or equal to 2, then this thing is always a solution. So that gives us a family of solutions which look like this. So we've got b, and then we've got b squared plus 1, and this is going to be for b bigger than or equal to 2. Okay? And then we've got the companion version, which is b squared plus 1, which is from switching a and b like we discussed much earlier. And again, that's for b bigger than or equal to 2. Now let's go ahead and check the case when b equals 1, because that's still allowed. So notice if b equals 1, this left-hand side is equal to 1 because we've got the floor of 1 over 1. And then let's go ahead and look at this right-hand side if b is equal to 1. So this right-hand side is going to be the floor of 2 plus 1 over 1 plus 1, but that's the floor of 3 over 2, which that's also 1. So if b is equal to 1, we also get a solution. So that means we can fill in this case is actually true when b is bigger than or equal to 1. So that's good news. So we check this out, and if m is equal to 1, we've got this solution. So now what we're going to look for is cases when m is bigger than or equal to 2. That's going to take a lot more work. Okay, so we've just gone through this case where m was equal to 2 in the equation that we derived where a was equal to b squared plus m. That gave us two families of solutions that are symmetric to each other. One was like b squared plus 1 comma b, where b is bigger than or equal to 1, so it can be any natural number. And then the other one was b and then b squared plus 1, where again, b was bigger than or equal to 1, so it could be any natural number. And I should say that these solutions are built off of the form like a comma b, where a comma b satisfy that equation up there. Now we want to look at the case, again, like I said, where m is bigger than or equal to 2. What we'll do is actually show that this does not yield a solution, and we'll do that by constructing an inequality which is never satisfied. Okay, so let's go ahead and recall that we had this equation. I moved it around a little bit, but we worked everything down to this equation. Now let's play with this equation until we have an inequality. So let's maybe go ahead and start with this part of the left-hand side, so b times m minus 1. So let's go ahead and notice that that is going to be less than or equal to b times m minus 1 plus m squared over b, the floor of that, because we're adding something that's bigger than or equal to 0. M squared over b is definitely bigger than or equal to 0. So next we can apply this equality to get the floor of b squared over m plus 1 over b cubed plus mb, and then I left off the plus m squared in the numerator. So we've got something like that. Now next, we can remove the floor function over on the right-hand side of that inequality, and that creates something that is larger than or equal to. So here, this is going to be less than or equal to this same thing without the floor. So we've got b squared times m plus 1 plus m squared all over b cubed plus mb. This is the inequality that we want to play around with. Most particularly this extreme left and right hand side. Okay, so let's maybe go ahead and clear the denominators here so it's a little bit easier to work with. So I can multiply the b through here, and that's going to give me mb minus b times b cubed plus mb is less than or equal to b squared times m plus 1 plus m squared. Again, that's just clearing the denominator. I didn't need to worry about a potential reversal of the inequality because we know that this b cubed plus mb is always positive. Okay, now let's expand both sides of this inequality. So here we'll get m times b to the 4th power, and then minus b to the 4th power. So that's by multiplying this b cubed onto both of these. And then next we'll have plus m squared b squared minus mb squared. So that's multiplying this mb onto both of those. Now we can expand out this right-hand side. That'll give us mb squared plus b squared plus m squared. Okay, sweet. But now we know that m and b are both natural numbers. So if we can set something up that is less than or equal to 0, then show that that thing is impossible to be less than or equal to 0, then we've found that there is no solution at all. So in other words, what I'll do is I'll move this stuff over to the left-hand side, and then I'll have a bunch of stuff is less than or equal to 0. And we'll see that that bunch of stuff being less than or equal to 0 will cause a problem. Okay, so let's see what we've got. We've got a couple of like terms. We've only got one like term, and that would be this guy and this guy. So I can subtract this if I put a 2 as a coefficient here. That's our only like term, so let's move everything else over. Okay, so we'll have mb to the fourth, and then let's see, minus b to the fourth plus m squared b squared minus 2mb squared minus b squared minus m squared is less than or equal to 0. Again, like I said, what we want to do is show that this thing over on the left is never less than or equal to 0, which will tell us that we don't have any solutions when m is bigger than or equal to 2. Okay, so let's see what we can do with this thing over here on the left. So let's maybe notice that we can factor an m squared out of this m squared times b squared minus m squared. That's going to leave us with b squared minus 1. So let's see, we've taken care of this term and this term, and everything else has a b squared attached to it. So notice that we'll factor out b squared, and we'll be left with b squared m minus b squared. So let's see, that would be like this guy right here, and then this guy right here, and then minus 2m from this one right here, and then minus 1 from this one right here. So we've got that is less than or equal to 0. Now let's see if we can manipulate this guy a little bit. So here I'm just going to bring this m squared times b squared minus 1 down, then we'll have plus b squared. Let's see how we can factor this. So maybe we'll put this one together with that one, because we can factor an m out of that. And that's going to leave us with m times b squared minus 2. That's good. And then let's notice that maybe we could combine that and that together and factor a minus 1 out. So we've got minus b squared plus 1 is less than or equal to 0. Okay, so at this point, we know that this term right here is always positive. And I guess I should say maybe not always positive, because b could be equal to 1, but it's always bigger than or equal to 0. But that means that this guy right here needs to be less than or equal to 0 in order for that whole thing to add up to something that is less than or equal to 0. Okay, let's take this inequality up and we'll work on this inequality a little bit. We reduced our current setup to this inequality. So we've got m times b squared minus 2 minus b squared plus 1 is less than or equal to 0. Now I want to recall over here that we're assuming that m is bigger than or equal to 2. So let's see what that tells us about the possible values of b. So I'll go ahead and just start with the left-hand side of this inequality. So m times b squared minus 2 minus b squared plus 1. So that's going to be bigger than or equal to 2 times b squared minus 2 minus b squared plus 1. So I get that just by replacing m with 2, because again, we're in the setup where m is bigger than or equal to 2. But now we can notice that that's 2b squared minus b squared, b squared. So minus 4 minus a minus a 1, so that's going to be b squared minus 5. Okay, so but notice that this is bigger than 0 if b is bigger than or equal to 3. But that would be bad for our case. We don't want this thing to be bigger than 0 because we want this whole quantity right here to be less than or equal to 0. So what that tells us is that b equals 1 or b equals 2. Okay, so let's look at this case right here when b equals 1. And I'm not going to check this super carefully because if you plug b equals 1 into the original equation, what you'll see is that you'll have to have a equals 2. So here we have a equals 2, but that means that m equals 1. But that's kind of a contradiction from our current setup. So you can think about this in one of two ways. We have either retrieved this solution right here with b equals 1 if we kind of forget about that m had a restriction, or since we're working under this restriction right here where m is bigger than or equal to 2, we have come up with a contradiction. Okay, good. So now what we can do is look at the case when b equals 2. But now if we throw b equals 2 back up here, let's see what we get. So we'll have 2 times m minus 1 plus the floor of m squared over 2 equals the floor of, so let's see, we're going to have 4 times m plus 1 plus m squared, and that's going to be all over. So let's see, that's going to be 8 plus 2m. So 8 plus 2m, like that. Now we can play the same game that we did to put something smaller than this left-hand side. So notice the 2m minus 1 is smaller than this left-hand side because we've just like not included this m squared over 2. And then let's see what is bigger than or equal to this right-hand side is just like getting rid of this floor function. So getting rid of that floor function, that's going to give us 4m plus 4 plus m squared over 2m plus 3. So now we've got this inequality to work with that involves m. Okay, so let's bring that up. Okay, so we're working in our current setup where m is bigger than or equal to 2. That implied that b was equal to 2. And then we reduced our equation right here, which came from our goal equation, to the following inequality. I think I had a typo on the last board with the inequality. This should be 2m minus 2. Now maybe we'll get rid of the denominator so this is a little bit easier to analyze. So I just want to reiterate, we want to find all of the m values that satisfy this inequality while simultaneously satisfying the inequality that they are bigger than or equal to 2. Okay, so let's maybe get to it. We've got 2m minus 2 times 2m plus 8. That needs to be less than or equal to m squared plus 4m plus 4. We're going to just do standard calculations here involving quadratic functions. It's really not anything too fancy. So let's multiply this out. We'll get 4m squared minus 4m plus 16m. So that's going to be plus 12m, and then next minus 16. So that's what we get from the last terms. And then this is less than or equal to m squared plus 4m plus 4. Go ahead and move everything here over to the other side of the inequality. That'll give us 3m squared plus 8m minus 20. And we want that to be less than or equal to 0. We can do this a number of different ways. Maybe let's solve the equation. So let's solve for the roots. 3m squared plus 8m minus 20 equals 0. You can see that this is not factorable, so we have to use the quadratic formula. We'll get two solutions here. We'll get m equals, so I'll just write them down. It's 2/3, and then minus 2 plus minus the square root of 19. Well, notice that neither of those are natural numbers, so this doesn't give us some strict inequality. It just gives us some sort of loose inequality. Well, let's get a handle on these two. So if we take minus 2 minus the square root of 19, well, that's going to be negative. So, of course, if m is bigger than or equal to 2, then it's already bigger than something that is negative. So that means all we need to do is look at this setup right here. And I guess I should say that this inequality right here holds for m on this interval, which is given by 2/3 minus 2 minus root 19, and then 2/3 minus 2 plus root 19. So we're looking for all of the m values that satisfy inside of that interval and bigger than or equal to 2. Okay, but what that tells us is that m is less than 2/3 and then -2 plus the square root of 19. That's what it takes to be inside of that interval. Being inside of that interval is the only way for this to be negative. And again, it's like an upward facing parabola. That's not too hard to see. But notice this is less than 2/3 times -2 plus the square root of 25, where I've just replaced that 19 with a 25. That gives me something bigger. But that's going to be equal to 2/3 minus 2 plus 5, because the square root of 25 is 5. But notice that gives me 3. I've got 2/3 times 3, so that means I get a 2 here. So if you check out what we have now, we have m has to be bigger than or equal to 2, and m is strictly less than 2, which tells us there's no more solutions. In other words, we don't get any solutions when m is bigger than or equal to 2. So we found our only solutions, and it's these over here. And that's a good place to stop.